Welcome back to this unit on thermodynamics, and as we have seen in last lecture that we have talked about criteria for spontaneous processes and we introduced the concept of entropy, and today we will introduce the concept of Gibbs free energy. Now, just to recap what we learned in last lecture, we learned that some processes are spontaneous and some are non-spontaneous. Spontaneous processes are the process when the process has a process which has I'll write that thing, a spontaneous process means that the process has a tendency or potential to occur without any external assistance. Now, we gave you examples of several spontaneous processes, and if you have noticed that we are using the terms tendency or potential. What happens in some processes are thermodynamically spontaneous because they can do or carry the process can be carried out without help of any external assistance, but their rate are so slow that with a small time frame or a normal time frame you probably will not be able to see any significant process happening. So, in that case apparently the process is not spontaneously happening, but the process has a tendency to occur without any external assistance. Now, the reverse process of spontaneous reverse of any process with reverse of spontaneous process is a non-spontaneous process, which require work need to be done from outside to carry out the process, and we gave you example also. Now, we talked about what are the criteria for the spontaneous processes, and we found out that decrease in energy of the system is not a criteria for a process to happen spontaneously. Now, we are only talking about energy of the system because we know that the total entropy of system plus surroundings cannot decrease. You cannot change the energy of system plus surroundings. So, we are talking about only look at the system, that decrease in energy of the system cannot be a criteria for a spontaneous process, and we gave you several examples like endothermic process where the energy exothermic process where actually the energy system loses energy. It might happen spontaneous, but in case of endothermic processes where system gains energy, still the process can happen spontaneously. We talked about many endothermic processes in the last class. So, what we found out after deliberation that increase in increase in randomness or disorder or chaos, whatever you can call, meaning the meaning you should know the meaning, disorder of system plus surroundings, which sometimes call totally, these two together is called universe. So, increase in randomness or disorderness of, or disorder, whatever you call, disorder of system plus surroundings should increase in a spontaneous process. So, we quantified this degree of randomness or disorder in a system as S, which is entropy. We define it as a entropy, which is extensive quantity state function. So, value of delta S does not depend on path, depends on path. Now, we have also seen that if we increase, so if we add some energy in the system, if we just talk about system, then if we add some energy, so Q is greater than 0, then entropy of the system increases. So, delta is system positive, and we also had discussed that if the same amount of Q is added at lower temperature, then the change in entropy is greater than the same amount of energy is added to the system at a higher temperature. This is what we observed, which means we have discussed last time that delta S should be inversely related to 1 over T, so or with temperature. So, this is what we discussed earlier, that if you increases, if you add some energy to the system, system's entropy increases, and if you add that same amount of energy at lower temperature, then the increase in entropy more than if you add the same amount of energy at higher temperature. Then we went on and found and set the relationship between this Q and temperature with del S, and we wrote this Q reversible by T. Now, for system, we can write del S system sys, Q reversible for sys, and temperature of system. For surroundings, I can write delta S surroundings is Q reversible surroundings by T surroundings. Now, because surroundings is very large, for a system surroundings is always very large. So, whatever energy is added to the system always happens reversibly. So, it does not matter whether the process which is undergoing in the system is reversible or not. If there is a heat exchange between system and surroundings, whether the surroundings loses some energy or gains some energy, surroundings will always do reversible. From surroundings point of view, the heat exchange is always a reversible process, because if you add some 100 calorie or 100 joule to the surroundings, it does not matter. Surroundings is so large that whatever amount of heat you take out or you add, it happens reversibly. So, if you talk about a process where Q is, so we can write this as minus Q of system, because we know from first law, as we discussed in the last class also, that surroundings energy change is exactly opposite to the systems. So, minus of Q surround system, and if we consider that the system and surroundings are at thermal equilibrium, if system and surroundings are at thermal equilibrium, this happen when they are separated by a non-adiabatic or diathermal wall. Then obviously, when they reach equilibrium, the temperature of system and temperature of surroundings would be equal at equilibrium. Then obviously, we can write T surroundings is same as T system. So, this we can write when system and surroundings is separated by a non-adiabatic wall, and at equilibrium, of course, system and surroundings will be equilibrium, which means T surroundings will be same as T system. So, I can write del S surroundings as this. Now, what we will do from next time onwards, for a system we will omit this term, this superscript. For system we will remove this superscript, and for surroundings we will keep the surroundings, and for total we will write TOT total as a superscript. So, if I write delta S or Q or T, then you will assume that these are for system. Now, if I want to specifically mention delta S for surroundings or T for surroundings, then I will write delta S surroundings or T surroundings. These are for surroundings, and if I write total, say del S total TOT, which means it will be delta S system, I am not writing system, plus delta S surroundings. So, this is the convention is followed. If there is no superscript on any of these thermodynamic terms, then you will understand that these are meant for system, and if we specifically talk about total or for surroundings, then the superscript of surroundings or total is added. So, one more time, if there is no superscript subscript is added to any of this term, then you can assume that we are talking about this for the system. So, if I now write here, we can just write delta S system is Q reversible by T. I have removed the system terms, and delta S surroundings would be minus Q. I am removing system term and then T. Okay. So, I will come back and rewrite this in the next page. So, delta S surroundings is minus Q by T, and delta S, which is delta S for system, U Q reversible by T. Q reversible means it is the exchange of heat energy in a reversible process. If I will come back and describe this little more in a minute. We will talk about for surroundings. If I talk about a adiabatic wall, then obviously this will be T surroundings, but what will be the value of Q? Q is 0, because for any adiabatic process you know Q is 0, then delta S surroundings is 0. So, for any adiabatic process, or if system and surroundings are separated by a adiabatic wall, then delta S surroundings would be always 0. Please remember, for any adiabatic process, no matter what is the process, because there is no heat exchange, Q is 0, delta S surroundings would be 0 always. So, we will now go back and look about system or focus on system. Now, what is Q reversible? Q reversible is if the process from state 1, if I have something like P 1, V 1, T 1 to some other P 2, T 2, V 2. Say I have these two states, this is state 1 and this is state 2. Now, actual process can bring about this change in any way. In obviously, if the spontaneous process will be a irreversible process, as we mentioned in the last lecture, that all the processes we see in happening spontaneously in real time, they are all irreversible process. So, in practice, the change from state 1 to state 2 will happen irreversibly, but what we have to find out? We have to find out from the given condition, from given information, we have to find out what is state 1 and state 2. Now, that is what we need to find out at beginning from the given information, and once we find out state 1 and state 2, then you have to imagine any possible reversible path between 1 and 2, and for that you can find out Q reversible and you can get del S from Q reversible by T. We will go back and look at that simple example we had talked in last class, that we have say state 1, we are talking about say the expansion of ideal gas adiabatic process, adiabatic. Let us this simple process. So, I have this side, this is adiabatic. So, it is surrounded by a adiabatic wall. So, no heat exchange is possible. Now, this side volume is V 1 and this is V 2. Now, at beginning we assume that this is P is equal to 0 and this is some pressure P 1 and this is some temperature T 1. So, that is state 1, and then what we are doing in state 2, we are removing this barrier between this part and this part. So, what will happen? Obviously, the gas which is ideal gas, we can take a specific sort of free expansion here, you can write free expansion, because we are talking about P is equal to 0, external pressure is 0. So, what will happen now? The volume would be V 1 plus V 2. What will be temperature? Pressure will be different. So, it will P 2. What will be temperature now? Remember, this is Q is equal to 0, this process Q is equal to 0. W is equal to 0, expansion into vacuum, free expansion. So, del U must be 0, and as soon as del U is 0, we are talking about ideal gas, you know del T is 0. So, here also it will be T 1. Okay. So, now I got state 2, where I know what is P, P 1, P 2 and V 1, what is the volume, total volume V 1 plus V 2. So, this is the first work you have to do, you have to just find the process. Given the process, this is given free expansion of ideal gas in adiabatically. So, in this case you have found out that what are the two steps. Now, Q is 0. So, delta S surroundings is obviously 0. As I said earlier, the adiabatic process, you will see delta S surroundings is 0. Now, this is actual. For surroundings, one more time, it is the actual Q which matters. For surroundings, the actual, please consider the actual Q. Here the actual Q is 0. So, when you, one more time I am writing, surroundings is minus Q by T, this Q is the actual Q involved in the process. Okay. But in the system's case, it will be Q reversible by T, okay, where you have to imagine that from state 1 to state 2, the process happened reversibly. In this case, this free expansion, it actually happened irreversibly, but now you have to imagine that system has gone from state 1 to state 2 reversibly, and then you have found out what is Q reversible. Now, what is W in reversible expansion from a volume V 1 to V 1 plus V 2 is given by minus nRT ln V 1 plus V 2 by V 1. The original, this is the my state. So, original volume was V 1, new volume is V 1 plus V 2. So, I can write final volume V 1 plus V 2 by initial volume is V 1 minus nRT, because it is a reversible, we are talking about reversible. So, I can write W reversible. Del U is 0 in this case, because there is no temperature change. So, obviously, Q would be minus of W. So, nRT ln V 1 plus V 2 by V 1. So, del S system, this is Q reversible, system is Q reversible divided by T be equals to nR ln V 1 plus V 2 by V 1. Please remember what I did, I just again repeating, the actual process is not a reversible process, it actually free expansion. So, it is a irreversible process. So, by knowledge of the actual process, I found out what is the initial state and what is the final state, and what is the actual Q involved. Actual Q we have used for calculating del S surroundings, but for system, once you know state 1 and state 2, you have to imagine a process, reversible process from state 1 to state 2. So, I would imagine now that a gas having initial state of P 1 T 1 V 1 has expanded to state 2, where temperature is T 1, pressure is P 2, some other pressure, and volume is V 1 plus V 2. So, this is the process. So, now I will put W reversible is this, and because we know del U is 0, isothermal expansion, adiabatic process, ideal gas. So, del U is 0. So, Q reversible would be minus of W. So, this and delta S system would be, or we can write, just write delta S, it will be Q reversible by T. So, this is V 1 plus V 2. Now, you can see that this is always positive, as long as V 1 plus V 2 is greater than V 1, delta S system would be greater than 0, and delta S surroundings is already 0. So, total would be depend upon delta S system. So, in this case you can see this is a spontaneous process, and delta S total system plus surroundings is turned out to be processes. So, any expansion process of gas will result into a total entropy change positive and total positive interchange. So, that is why it is a spontaneous process. So, again one more time I will explain. For surroundings you have to get the actual Q in the process and then use this formula. For system you have to find out what is state 1 and state 2 from the given information, and once you get state 1 and state 2 you have to imagine a reversible path between state 1 and state 2, and then you have to find out Q reversible in that process, and from then apply this formula to get the system's entropy change. Now, we revisit our criteria for spontaneity. This criteria for spontaneity, criteria for spontaneity is delta S total is greater than 0, which means delta S system plus delta S surroundings is greater than 0. We are not writing anything on system now. And what is delta S surroundings is minus Q by T surroundings greater than 0. Now, if I apply first condition where I think system and surroundings are in thermal equilibrium, then T surroundings is same as T system or just T for we do not want to write system. So, just T, then I can write this turns out to be delta S minus Q A by T greater than 0. Now, we apply our second condition where pressure is constant. In this process pressure is constant. So, Q is Q P, we know Q P is del H, then we can write del S minus del H by T is greater than 0. On rearranging we can write del H minus T del S less than 0. Now, we will put third condition now or third restriction where temperature is constant. If temperature is constant, then we can write this as del H minus del T S less than 0 or H minus T S less than 0. So, what did we do in this page? We knew, or by this time we know what is the criteria for spontaneity, but in this case criteria has both entropy change for system and surroundings, but we do not want to always deal with surroundings, is always difficult to handle with surroundings. So, we want to get some conditions where we will only look at the system, values corresponds to system, but that will not come for free. We have to apply or we have to put some restrictions to get some value only for a criteria for we can get some criteria for spontaneity only for system, and this is what 3 restriction we have applied from this case, and we got finally this value. Now, this is all for system. So, there is no term which is related to surroundings here, but to achieve these conditions we have to put 3 restrictions: system plus surroundings are in thermal equilibrium, pressure is constant and temperature is constant. But in most cases what happened, we deal in practically we deal with systems or any process happening in diathermal wall, non adiabatic wall. In that case equilibrium condition will always be where system plus surroundings are at equilibrium. So, this is this condition is often met. So, we generally mention this condition most of the times. So, we only talk about pressure constant and temperature constant. So, from now onwards I will just omit this condition, because this is assumed to be happening for when the system is not adiabatically surrounded, and as you know, if this is surrounded by adiabatic, then its surroundings entropy change is anyway 0. So, we will deal with only system if system is surrounded by adiabatic wall. If it is not surrounded by adiabatic wall, non-adiabatic wall, then automatically at equilibrium we will get the thermal equilibrium between system and surroundings. So, temperature of the system will be same as temperature of the surroundings. Hence, we consider this is a given condition. So, we will mainly deal with pressure constant and temperature constant. So, we know what is the criteria for spontaneity, that del of H minus change in H minus Ts is less than 0, and condition it we will put only on constant temperature and constant pressure. So, that is the conditions. Now, to make it simpler, we mathematically define a new term G as H minus Ts. So, we can write delta G less than 0 at constant T and P. So, this is the conditions for spontaneity. Delta G is less than 0. So, G should decrease in any process which is happening at constant temperature is process, for the process to happen spontaneously. What is G? G is we call it Gibbs energy or called Gibbs free energy. This is again extensive quantity, extensive parameter state function. So, del S value of del G will not depend on path like other thermodynamic parameters. Now, G is called free energy because I am not going in detail. The value of G is signifies the actually it's the available energy to or free to do non-expansion work, non-PV work, or we call other work or additional work, like electrical work, magnetic work, those work. So, you will see its significance when you study electrochemistry. So, that is why this term free energy comes. So, this is the part of the energy of a system which is free to do non-expansion work or additional work. So, the term free comes. So, that is why it is sometimes used Gibbs free energy. Now, at equilibrium, if the process reach equilibrium, we know, we have seen earlier that total entropy total is 0 when at equilibrium. So, in this case for system it will turn out to be delta G is 0 at constant temperature and pressure for system in equilibrium. So, this is the process condition for spontaneity, and this is the condition for equilibrium. So, clear. Now, we have from the main conditions which we got it from our experience, that total entropy of the system should increase in a spontaneous process. We landed up expression only for system where the Gibbs free energy of the system should decrease at constant temperature and pressure to have a spontaneous process happening, and if delta G is 0 at constant temperature and process pressure, then the system has reached equilibrium. So, G is minimum when the G will have a minimum value when the system will reach equilibrium. Similarly, the entropy of the universe is always increasing or maximizing when we talk about the spontaneous processes. So, we will go back and write delta G is equal to delta H minus T S. So, if I consider a constant temperature process, then we can write simply del G is equal to del H minus T del S. This is we are talking about constant temperature. So, please mind it. So, for a chemical reaction, we can write similarly standard Gibbs free energy for reaction delta G naught is equal to standard enthalpy of reaction minus T standard entropy of reaction. So, this expression we can write at constant temperature, Now, this will from this we can if there are a lot of cases these values are known. So, from we can just analyze this expression to find out the type of reaction which will become spontaneous, and in this case temperature will play a lot of important role. Just we will go back and see what the possibilities are. So, the possibilities are, we will make a table. So, these are the possible expressions, combinations where standard enthalpy of reaction is less than 0, negative, and this is positive. Remember what is the expression? Delta G is del H minus T del S. If this is negative, delta is positive, then del G must be a negative term irrespective of what is the temperature, and we know when this becomes negative at constant temperature and pressure, this process become spontaneous. So, this is spontaneous at all temperature. Now, if I get the other condition, this is negative and this is also negative, then temperature, this is negative, this is negative. So, this term is negative and this is actually positive term. So, depending upon temperature, value of temperature, the sign of del G will get determined. So, if temperature is low, this term will dominate. So, it will become negative. So, this is 0 at low temperature and this is positive at higher temperature or high temperature. Now, this is relative, low and high are relative. So, this will be, if this is the case where both standard enthalpy of reaction and standard entropy of reaction are negative, then it is likely that the process of the reaction will happen spontaneously at low temperature, and it is likely that it will be non-spontaneous, it will not happen at high temperature. We can now consider the other one where both are positive, then the situation will reverse, then it will be positive at low temperature and negative at high temperature. So, in this case will likely to have a spontaneous reaction at higher temperature, and if we get the situation reverse of the first one, where delta H is positive and delta S is negative, then this is a positive term and this is also a positive term, because this is negative quantity, then it will be positive. So, in this case this is non spontaneous for or at all temperature. In this case this is spontaneous and this is spontaneous, this is non spontaneous, this is non spontaneous, and at any temperature, at temperature which del Z standard in becomes 0 or del Z become 0, that is when at constant T and P, that is why we will reach equilibrium. So, if we consider one any chemical reaction A plus B to C plus D, then the criteria for equilibrium, criteria for this reaction to reach equilibrium, criteria for reaching equilibrium would be delta G for the reaction is 0. Okay. So, once it reach or G minimize in this reaction, it will become it will reach a equilibrium situation. Now, we can show that this is linked to at equilibrium. We can directly write, it can be shown that at this is 0 equals to the standard gives free energy change in the reaction plus R T ln K, where delta R G naught is the standard gives energy change in the reaction and K is equilibrium constant at that temperature where it is happening, reached equilibrium at T. So, if you know, so any case if we know the any of the terms, we will be able to find out the other term. If we just go through a problem, then we will be probably able to see. So, where say in a case where delta Z0 is given, this is from your book, delta naught the standard gives free energy change is given as 13.6 kilojoule per mole at 298 K. Then the equilibrium constant we can find out from this expression. We can find out equilibrium constant from this expression, which is minus dot divided by R T ln to just R T log we have taken. So, 2.303 R T. So, you can just solve this equation to find out the value of equilibrium constant. Now, I think this is what we need to cover in terms of topics we have covered, and now I think I should go back, whatever time is remaining, I will just look at few problems quickly and see whether your just to revise your knowledge one more time. So, just as I will not be repeating or revising this last portion, I just wanted to go back and revise it one more time. because this is likely to be the last lecture in this unit. So, in this case we from the condition of spontaneity, which is delta S total or entropy change for universe should be positive, we landed to a condition which is only related to system, where delta G should be negative at constant temperature and pressure, and delta G is a mathematical description of this quantity H minus T s G, which is called Gibbs free energy or Gibbs energy, is extensive quantity state function. So, delta G will not depend on path, and we talked about delta G at constant temperature is del H minus T del S, and from that we found out that these are the possible options. So, if we assume these are all happening at constant temperature and pressure, and these values are not changing in that if we change the temperature. So, which means this will happen at small this will happen if the reaction enthalpy, standard reaction enthalpy is negative and entropy is positive, then it will happen spontaneously at all temperature, and we discuss the other possible conditions. So, now I think I have about 15 or 10-15 minutes. So, I will just quickly go through few of the questions which is there in your book, and I will stop as soon as the time ends. These are from your book. So, this multiple choice question, it says thermodynamic state function is a quantity used to determine heat change whose value is independent of path, used to determine pressure volume which value depend on temperature, but we know the thermodynamic state function does not depend on path. So, this would be your answer to. For the process to occur under adiabatic condition, Q is 0, adiabatic condition, W is 0, there is no volume change, delta T 0 is the initial temperature and final temperature is same. It does not mean there is a isothermal process. Delta P is 0 does not mean there is a isobaric process, it just says the initial pressure and final pressure is constant, but adiabatic condition always will have Q is equal to 0. The third question is the enthalpies of an element in their standard state. Now, this question is little ambiguous. I think the question should be framed like this: the standard enthalpies of formation, okay, is this term is missing. This should be standard enthalpies of formation of element in their reference state, that is 0. But this is none of this answer could be a right answer for this particular question, though some of will suggest that it is 0, but it is not 0. Enthalpy of all element in their standard state is not always 0, it is not in fact 0, because we know what is standard state. Standard test for liquid and gas, for liquid and gas is corresponds to a pure state. Pure pressure is 1 bar and a particular temperature T. So, all elements, if you are talking about liquid and gas, any pure element will not have enthalpy is 0 at 1 bar pressure or at any temperature. For gas, so liquid and solid and liquid. For gas, we have to have additional criteria that the gas would behave ideally in this pressure, which is not possible. So, it was for gas, it is a fictitious state. So, I think this is not neither of this is a right answer, but I think this question should be framed the standard enthalpy formation of all the elements in their standard state. We will move to the next question. It says del H, some values is given, find the value of del H, combustion of methane. Combustion of methane is just burning of methane and you are getting CH2 plus CO2 plus H2O. You can balance this, maybe this and this. This is gas, this is gas, this is gas, and this is liquid. So, in this case delta N gas is equals to 1 minus 3. So, minus 2. This is 1 post, and before it is 3 moles. So, delta N minus is minus 2. So, del H would be del U plus delta N G R T. So, del U would be delta U minus twice R T, which means del H would be greater than del U, no matter what is the value. It could be negative or plus, but this would be always greater than del U if del N G is minus. If it is a positive quantity, then del H should be, sorry, in this case del H, yes, del H should be, because some del H is equal to del U minus something. So, del H should be less than. So, del H is del U minus something. So, del H should be less than del U. If this is a positive quantity, then del H should be greater than del U. Okay. So, you have to just look for this expression, find out del N G, and from that you can find out what is the relationship. In this case, it says some energy is produced. Once the energy is produced to have a positive entropy. So, in this case, if we talk about think about constant temperature and pressure, then Q is equivalent to del H. So, del H is some energy is released. So, del H is negative exothermic process and positive entropy change. So, del S is positive. So, now you can go back and look for, find out, you yourself can find out what is the temperature low or high, where this should be negative. The next question is from your book again, and this is 701, heat is absorbed by the system. When some heat is absorbed by the system, Q is positive. So, this is 701 joule, and 394, work is done by the system. When work is done by the system loses some energy. So, W is minus 394 joule. So, the internal energy should be summation of these two quantity Q plus W. You can do later on. This is calculate the enthalpy change of freezing of 1 mole of water at 10 degree cent ice at ice to this. So, you have 3 process, one 10 degree centigrade water to 0 degree centigrade water, and then freezing water to ice at 0 degree centigrade, and then 0 degree centigrade ice to minus 10 degree centigrade ice. So, these are the 3 process where you can just total enthalpy change, you can add up the enthalpy change for all the 3 processes, and if we consider these are independent of temperature in the 10 degree gap we have, then we can find out in this case Cp of H2O liquid, and we are talking about 1 mole. So, N is 1, it will be Cp multiplied by del T, in this case del H. In this case it is fusion, fusion means melting. So, this will be a reverse of melting. So, it will be minus 6.03 kilojoule per mole, and similarly it will be Cp H2O solid into del T. So, you can add these 3 term to get the value for the total enthalpy change for this reaction. So, here it says the enthalpy change of formation of the 4 quantities are given and you want to find the value of del HR. Now, we know del HR is equals given by summation of AI and delta H formation of reactant products minus BI for reactants. So, in this case all the values are given for, now remember these values are for 1 mole, the definition enthalpy of formation, standard enthalpy of formation for 1 mole. So, whenever there is 3 mole, you have to multiply it by 3 and then just use these expressions to find out the change of a total enthalpy. In this case the enthalpy change is given for this reaction. So, what is the standard enthalpy of formation of, now these are the there is no temperature given. So, I will assume 298 K is given is the temperature of this process, and in 298 K the reference state of nitrogen element is nitrogen gas and hydrogen is hydrogen gas. So, this is fine. So, this reaction is formation of ammonia from their reference state, but mind it here it is 2. So, it is 2 mole, but the formation is for 1 mole. So, in this case the enthalpy of formation would be half of this reaction, half of this value, because you are forming 2 moles. What you need to find out for 1 mole from this reference state. So, this value will be just half of the case, and this is I think we can apply the Hess's law using this formation reaction. In this case, you should mention I think CCl liquid, this should be a liquid. So, delta H evaporation will be CCN for liquid, and you I think I have just gave example of this type of Hess's calculations from Hess's law. So, from which you can get the expression from the value of del HR of this. So, 1/4 of that value would be the bond enthalpy. I do not have time, so I have to stop. I think I had many more questions to discuss, but unfortunately because of time I am not able to do. So, what I will do, I will stop here and just say that I hope you enjoyed this course on thermodynamics, and in case you have any question, any doubt, you are free to do so. You just send me an email or contact me. I will be happy to answer your questions, and my contact informations are available in the website of Chemistry Department of IIT Kharagpur. So, good luck.